So welcome and good morning to our 10th week for type systems and correctness and security. Today we're going to have an interesting topic from the Advanced Topics in Types and Programming Languages book. We're going to talk about typing low-level languages, but before we do so, as usual, we will get started with the exercise. So, exercise number 8 was on subtyping. Just quickly pull this up a bit. Should work. Yeah. So, the first exercise was to write a short program that will fail with the runtime type error. That means that its evaluation will get stuck if the first premise sref is dropped. And then write another program that will fail if the second premise is dropped. Okay. Let us quickly pull up. Didn't plan on doing so, but as we're in there, let's quickly pull up the slide for that. That was slide 18. And that's probably the wrong reference. No one noticed that before. Interesting, that's also the false week. That was week 7. My voice is very low today. Let me quickly check if I can turn things up a bit. Oh yes, I can. So this should now be a bit better than before. Okay. Good. So first thing, the reference in the exercise was apparently not correct. No one noticed that before. Okay, so it is actually week 7, slide 18, and that's this rule. So this is the sref rule that is mentioned here in this exercise. So whenever we have S1 as a subtype of T1 and T1 as a subtype of S1, then the reference of S1 is also the subtype of the reference of T1. It's the invariant definition of subtyping for references. Okay, now the exercise is that we write a short program that will fail if the first premise is dropped, and then we write a program to fail if the second premise is dropped. Okay, let's switch back to the other mode. Good. Yeah, for some reason my microphone keeps resetting over the week, and I have to remember on the checklist to set it up to full volume during the week, like when I start the lectures. Good. So evaluation will get stuck for if the first premise is dropped. Okay, let's try something that will fail if this is the case. Good. So let's make a first term. So we're in the first part of this exercise, and let's make a first term called T1, and let's make things like this. So x is 12 and y is 13, and let's say this is type T1. We can always do that, and let's do a second one that is also x12 and y13. Could be other values, of course. but in this case it's the case, and Z is 42, and this is a parenthesis, sorry, I never could draw them correctly. So and let's say this is T2, yeah, and by SRCD width, we know that T2 is a subtype of T1, yeah, because this thing is a little bit longer than this, so it can be a subtype of this. Yeah? Okay, so the first idea was to drop the first premise. So the first premise is S1 subtype T1. Good. And for this, let's write a program that does that. And nothing could be easier. We say that X is a reference to T2. We could easily do this with a let. I'm doing this with sequencing here, same thing. And then assign to X T1, which we can now do because we dropped this premise here. And then the last thing in the sequencing that we do now dereferencing, and of course project to Z, because T1 does not have a Z. This should get stuck, and it actually does. Type-wise, this would be okay because we dropped the first premise, and then we would come that this won't evaluate. And then we'll have the opposite case, that when we drop T1 subtype S1, then it would be that if we say X is a reference to T1 now, and we do the vice versa assignment, X is now T2, and then we will do this. This will of course evaluate. Yeah, it would progress, but it would not type check. Yeah, would not type check. So this is why we need invariance, because in the one case we would have programs that would not evaluate, and in the one case we would programs that would evaluate but would not type check. That would be overly pessimistic in this case, and this is not the case. Yeah? Good. And of course you could construct other programs that will have the problems in the opposite case, and so on and so on. This is not the only solution for this exercise out there, but you probably already guessed that. Okay. Questions up to this point, maybe? Doesn't seem to be the case. Then let's move on a bit to the next exercise. So the 8.2 exercise was all on algorithmic typing. Good. So algorithmic typing. With the definition of algorithmic typing of slide 41 on week 8, which should read week 6, I believe, week 7, I believe. Quickly move to slide 41. Yes. So this is the slide referenced if you do not know. So the definition number you see down there in the bottom right corner, and it's slide 41 in week 7, not week 8. Gotta correct this. Good. With the definition of algorithmic typing, show that the type assigned to a term by the algorithmic typing rule can decrease during evaluation by finding two terms S and T with algorithmic types S, big S and big T, such that S eventually evaluates to T, and T is a subtype, big T is a subtype of big S, but S is not a subtype of big T. Yeah, so something that actually provides a decreased term, a more precise, decreased type, a more precise type than before. Okay, let's switch back. Good. How do we go about this? Well, let's formalize this a bit, what we have in this exercise. So 8, 2, 1. Good. So what do we have there? We have S, which is of type big S, and we have T, which is of big type, type big T. Oh. And we already know that S evaluates eventually to T. No? And what should we find? We would find S and T such that T is a subtype of S, but S is not a subtype of T. So what's the first insight? We need to check. We need something that like is a decreasing type. And think about what the only point was where we would actually have decreasing types. If you go back to the lecture slide here again, where's the only thing where we actually have decreasing types? So anything where subtyping relations were actually in it. And as you can clearly see, it's the T-app rule. The T-app rule is the only point. You see there the premise in the middle. That's the only point where we actually have decreasing types. The other rules don't even mention subtyping at all. So the only rule that should be very interesting for us now to play around with is the T-app rule. Okay, so let's do this. So let's just write it down. So the TA, algorithmic typing, the TA app rule is seems to be interesting. And we have to check for that. So if the T-app rule is the thing we want to play around with, then let's make our terms in the form that we actually have an application. So we're free to find S and T in the way we want. So let's say that S is an application of S1 to S2. We can kind of decompose this. And of course, the output of this, because it is equal to S, must be of type big S because we forced that up here. No? So that means that there is S1 and let's say S1 goes from S11 to S12 because it's a function. It's the left part of an application, so it needs a function type. No? And what we see here, the resulting type is S and S12, so S must be equal to S12. No? So we already bound the right type, which is pretty neat, so we already know what that should be. And then we need to think about the argument type a little bit. So let's take S2 and say S2 is big S2 typed. And then we need to find a compatibility between S11 and S2. Of course, we can force they're equal, but let's spice things up and make things a little bit more interesting because we want to find decreasing types. Yeah? Let's make a decreased type. So S2 is a more precise type than S11. But compatible. We can do this because we can do arguments to functions which are compatible with the input type. And that usually works. Okay, now we have constructed an S. So let's see if this works and if we can actually have this going for us. Good. So let's try to see what comes out of evaluation. So let's take the the evaluation rule, apps. Yeah. And from this we know that S1, S2 we can also write as something that takes an X that is S12 in the body and takes S2. So we can basically like unroll S1 here. And that evaluates to something where X is substituted by S2 in S12. So now we've decomposed this function into a variable in a body, which we can always do because we know it's a function from S11 to S12. We've set that, so we can also decompose it in this form. So we need to talk a little bit about S12 to be able to do that. So S12 is of type big S12 because it's our convention. And because of all of this is S again, the resulting type of this must be S. So we're free to choose S, remember that. So we can now say that S12 is X. So what basically comes out here is the identity function. So we're free to do that. And that implies some things. So we said that S12 would be X, but then what comes out? S1, sorry. So the type of the thing. So S1 would be, so it's the thing here up there. S1 would be this type of small s1, so S11 to S12. But also when we set S12 to X, we already know S1 needs to be S. S1 needs to be a type going from S11 to S12. We also know that S12 is S, so the right side is already S. But we also know that the input type is the same thing, so this is a function that goes from S to S. And then if we look at the substitution again, just to make things more clear, so X is substituted by S2 in S12. This is the thing we determined up here. Then we get S2, because it's the identity function. S12 is X, and X we substitute by S2, so we get S2. And then we would see that S11 is S12. And then we would see that this is would actually work. Yeah? It's naturally true by looking at it, but just to make things clear, I spelled that out here at this point. No? So now we go up here again, that S eventually evaluates to T. So S1, S2, which is S, evaluates, let's say in one step, we're free to do so, why not? Yeah. To T, and then we would see T must be T2. Oh. And from this it follows that T is a subtype of T11, and we know S11. Excuse me. And from this it follows that T must be a subtype of S. Hmm? This is kind of the theoretical construct that you do. You can also do this by example. I gave you a solution by example that uses again the insight that the TA app rule is the only thing where you are decreasing, and then you take basically some records and find the same thing. Good. Questions for the first part of 8.2, so the 8.21. Good. Not seems to be the case. Smooth sailing this morning. So let's move on to 8.2. So we already learned that when we see week 8 in this exercise, we have to think about it as week 7. So let's do this. Slide 43, that's not far ahead, is the completeness theorem for algorithmic subtyping. So the exercise was draft a proof for the completeness theorem for minimal typing. Oh. Good. Proof drafts are always nice because you don't have to spell everything out. So whenever someone requests a proof draft from you, you do not spell out every detail, but it has to be complete in that sense that we see that like the other person sees what you're going for. Good. How do we go about this? So how do we go with this? Of course, as any proof in this course goes, it's an induction on any kind of derivations or any structural induction. So what we do is, again, induction on the declarative typing derivations. And then we do a case-by-case process on the final rule in the derivation. Always think of this tree from the bottom. So think of the last rule applied, basically. Good. And then everything else by induction holds. So the first case as usual, is always the t-var case. So if you have the t-var case, then you have a form of the term that is like this. Yeah, so the term is a variable, of course, and what you also know that the type of this variable in the typing environment we assume is t. And if you now compare this with ta-var, this is rather immediate from ta-var. This is basically the same thing. Now, if you go back to the rules about that, oops, no, wrong window. If you go back to the algorithmic typing rules, you actually see this. So ta-var with the premises that we have here written down basically comes to the same conclusion. So you're good to go. Oh. Good. So next case is the t-abs case. And then, so we have an abstraction. So the term form is lambda x, which is typed as t1, and the body of the function is a t2. And what we also learned from the t-abs rule, that we can assume the premises again, and then under the assumptions of gamma, and that x is t1, you can derive that t2 is a well-typed term of type t2. And what you can also derive, that t, and this is just the type of the term as usual, is something that goes from t1 to t2. Yeah? This is only the premises assumed, as we know that we have the term right here, as usual in these proofs. So when you now take the induction hypothesis into account, then you know that under the assumption of gamma and that x is typed as t1, t2 is typed as s2 for some s2 subtype of t2. This is coming from the induction hypothesis that the completeness theorem holds for the subterms, and the subterm here in this case is the t2, and then you actually have solved this case almost, because then you say, okay, then you take the ta-abs rule into account, and from this rule you know under the assumptions of gamma that t is going from t1 to s2. And then you have to check the s-error rule again, because we have a function type here. And the s-error rule says that t1 to s1 is a subtype of t1 going to t2, and this is actually what we require. And this is actually what we required to check this case, and then we're good. By the way, this is a little bit more than a proof sketch. It's actually almost a proof. We would have to write this out a little bit for people to actually check it. It's a little bit of a shorter form, but in general that's sufficient, at least in this course. For papers you probably want to write it out for that people can follow your thought a little bit more better, because they typically don't have the audio track that I just give you. Good. So that was the t-abs case. t-var case we also checked, so let's add the check mark here too. Good. What else do we have? Of course, if we have function abstraction, we have function application. So it's the form of tapp. And in this case, t is t1 applied to t2. We can just decompose. And from the premises, we know that under the assumptions of gamma, t1 is a well-typed term, which is has a function type going from t11 to t12. What we also know that under the assumptions of gamma, t2 must be of that input type t11. And what we also know that the output type of the whole term of t would be t12 because it's the result of the function type. Good. Again, for the proof, we can use the induction hypothesis, the IH here. What we know from the induction hypothesis is that it is valid for that we have valid subterms. So under the assumptions of gamma, T1 is a type of S1 for some S1, which is a subtype of T11 to T12, if I'm not mistaken. Yes. And under the assumptions of gamma, T2 is typed as S2 for some S11 and S12, where T11, yes, is a subtype of S11, and S12 is of course a subtype of T12. Yeah, covariance and contravariance in function application is happening here. Okay, I might not be able to fit this proof for this case on this entire page. I have to really take care. Let's see. Now let's see. We can try. We can try to fit it. So what we also need is the inversion lemma. Yeah, so the inversion lemma for the subtype relation, that is 1532. Excuse me for a moment. Sorry. Good. So the inversion lemma for the subtyping relationship, that gives us that S1 must have the form of S11 to S12. That's given by the inversion lemma in this case. For some S12, S11. Did I mix things up here? I think I mixed things up here. Sorry for that. So the induction hypothesis does not give us this. The induction hypothesis... Yeah, sorry, I mixed things up. That's why I don't have enough space here. So the induction hypothesis gives us something else. The induction hypothesis gives us that, okay, T2 is S2 for some, yeah, okay, for some S2, which is a subtype of, yes, T11. Otherwise it wouldn't make any sense. Yeah, these things come later on in the inversion lemma. Good. So S1, we're now in the inversion lemma again. S1 has this form. And here now, this is the, sorry, I was mixed up while reading up on the notes. So S1 is going from S11 to S12 for some S11 and S12, where T11, now it all makes sense, is a subtype of S11 and S12 is a subtype of T12, and now the actual thing with the covariance and contrariance comes into play. Sorry for mixing that up, but it's the inversion lemma, and nevertheless it's true for this thing. So what you also have is transitivity that comes into play now, and transitivity says that S2 is a subtype of S11. Why is this the case? Because you see that S2 is a subtype of T11 and T11 is a subtype of S11. So by transitivity, S2 must be a subtype of S11. Sorry. Good. Completeness now gives us the following, that S2 is well typed as a subtype of S11. And I actually can fit it in here. And now you can take the T-app rule and say that under the assumptions of gamma, that is the case that T1, T2 is well typed as S12. And this finishes actually the case because we already have that S12 is a subtype of T12, namely up here. This is here from the induction lemma. We also have that, and we just found out that we have that. Good. Let's move on to the next case. So the next case in our proof, we need to take care of the record rules. So new case T RCD, and if we have T RCD, then the term has the form of a record. So L1 is equals T1 Ti, sorry, saying 1 and writing 1 actually, where I goes from 1 to n. And what we also have is that this thing is well typed. This Ti, all the subterms are well typed. Ti for all I for all I, and then T equals of course a record type that is Li as Ti, where I goes from 1 to n. Good. This is just again the rule inverted and shown as premises up here, because we now look at this case. And as you can see, this is pretty much straightforward because it straightforwardly matches to the record rule that we have here. It actually is more or less the same thing, because you don't have any interesting subtyping relation to check. So this is pretty, oops, so I switch back again. So this is straightforward, as we say. Okay. How does projection then work? This is our next case. T projection. And in this case, the term has the form that we have some record T1 and the label Lj. And we know from the rule that under the assumptions of gamma, T1 is typed as a record. So a record type Li ti I going from 1 to n, and the whole term must then be the jth type here in the record. And when you look in the rules again, you would find that this is pretty similar to the application case, actually, to show and prove, because you just select the subterm and you go about and then find that this is not very hard to show. So this is similar to application case. Again, in a proof sketch, this would be okay. If a formal proof is demanded, then it would not be okay. So in the proof sketch, I can just write similar to the application case and be fine with it, if it actually is. In a full proof, I would actually have to give this. So the next case, of course, and the final case is the T sub case. It's a weird way of writing a B. And for this, the term does not have a form. It just has a type called S, and we know that S is a subtype of T. And this actually follows from the induction hypothesis, and transitivity of subtyping. There you actually go. Good. This is the entire proof sketch for this 8.22. Any questions until this point, maybe? Not the case, obviously. Oh, yeah, where we have the... Can we also say that S1 is a subtype of T12? In which case are you right now? You probably are in the T-app case. Is that correct? And S1 should be a subtype of T12. Well, no. If you look at this particular point, is that from the induction hypothesis, we say, okay, T1 is of type S1. Okay, this is S1. And it's the type of the first thing. And this must be a function type. And this is a subtype of T11 to T12. And so I don't think it can be actually a subtype of T12 itself, because then T12 would also need to be function type. I hope that makes it clear. And then again, you see that, like, from the inversion lemma, you see that S1 must be something going from S11 to S12. It must be a function type. Cannot be T12 itself. Okay, great. Good. Then let's move on to 823. 823 function typing. So if we drop the error subtyping rule as error but kept the rest of the declarative subtyping rules and typing rules the same, would the system still have the minimum, that means completeness property, and if so, prove it, and if not, give an example of a typable term with no minimal type. No? Okay. In this case, I choose to find an incompatible term, so a typable term with no minimal type. Oh. And for this, I choose the following term. Lambda x is typed as a record taking an a, which is a natural number, and then using it as the identity function. And if we do not have the S-error rule, under the declarative typing rules, T would be, of course, A nut going to A nut, but also T would be A nut going to top. We could also do that using the subtyping, the T sub rule. This would work in with the S-error rule, but without the S-error rules, these types are then compatible by the S-error rule. But if you don't have them, these types are incompatible, and then you don't have a minimal type. And there's no type that lies beneath both of them. So this means we cannot drop. So this implies S arrow cannot be dropped. Good. Okay, before we take questions for this, let's quickly move on to the last one, as it's just a bit, and then we can take questions for both of them. Good. What is the minimal type of if true, then false, else empty record? And is this what we want in our language? What do we need to do? So in order to construct the minimal type, we would have to calculate the join. And the term that we have for this is false, which is bool, and empty record, which is an empty record type. It looks the same, but this is a term and this is a type. And what's the join of them? Well, the join of them is top. So that would be the minimal type of them. So this term is typable. So is this good in our language? Well, I wouldn't say so. I would say that's an actual weakness. It's hard to see that someone actually wanted to write that expression, that if true, then false, else empty record. Because also that, like, if true, if you can determine that statically, why bother with an if? But also if this, like, if the condition would be more complex, why write an empty record on this? Because then you would have a top type. If you do something like this in Scala, will assume this any type, this top type in Scala. We will think about the Scala type system also in this lecture. Not today, but in one of the upcomings. And it will assume the any type, which is basically the top type. You cannot do anything with that term anymore. You can use it and you can like dynamically check the contents and dynamically type that, but statically you cannot do that anymore. Yeah? And if you type this as top, then actually you cannot do any expression with that anymore. Yeah? Because top does not match anything else. So there's like little point computing that in the first place. So one, you can have like 2 responses to this weakness in your language design. This is a little bit an excursion, but one is you can simply remove top from the type system. Then you wouldn't find an upper bound type like a minimal type for this, and then you would also be good. But then again, what you can also do is you can make the join a partial operator. You need to make join then a partial operator, because then not in every case you would result to something. In the join operator, what you basically do is when you cannot find anything else, you result to top. You would have found that by implementing the current lab, actually, by the way. And the other one is you can keep top, and you can make your type checker generate a warning. When the minimal type of a join is top, then you would just output a warning and say, well, this is probably not what you wanted to do. In Scala, they follow the thing that they just resort to their top type, to their any type, and then later on, if you would use expressions that come out of this, you would see the actual problem. And this is how they deal with that. Okay, any more questions for 8.2.3 and 8.2.4? Probably. Okay, does not seem to be the case. In any case, just a quick reminder, you can always ask any questions afterwards in Panda. I would try to answer them as soon as possible. I know I have one open question for a previous exercise already open. Good, then let's say we do a 10-minute break until 11:06, and then we continue with the lecture. Good.
chapeau. Dab dab, vidi 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 va. Les rois touchent manus, morbid in the bar. Innocent sentimental mood of Venetus, Venetus. Ces soirées jouent dans l'air où les rois touchent manus. el suelo camina la tarántula. Ve con cuidado, por el techo camina la tarántula. La tarántula camina. Por el suelo, por el techo. La tarántula camina. Por el agua y por el fuego. La tarántula camina. Por tu espalda cuando duermes, la tarántula te puede picar. Desde el suelo vigila la tarántula. Ve con cuidado, desde el techo vigila la tarántula. La tarántula vigila. Desde el suelo, desde el techo. La tarántula vigila. Desde el mar y desde el cielo. La tarántula vigila. Desde dentro de tu mente, la tarántula te puede picar. Ponte la inyección. Si te pica la tarántula, no hay otra solución. Si te pica la tarántula, aprende la lección. La tarántula te puede picar.
Good, so welcome back. In today's lecture, we will talk about the types for low-level languages. So we are concerned today with languages that are not as sophisticated or as high up the chain as things like Java or possibly the Lambda calculus. So low-level languages, what is that actually? So let's have a look at compilations. So we call languages that you usually program in high-level languages. So things like C++, C, your languages that you developed, or Java, these are typical high-level languages because they abstract away from the underlying hardware. But eventually they will have to be running on this hardware, and one thing is to interpret them, but another way is to compile them. And compilation means that you translate these programs into the same program but in a low-level language. That is the XRD6 instruction set, the IA64 instruction sets, the ARM instruction set. There are like a bunch of instruction sets depending on the processor architecture and system you are working on. And this then runs on the bare metal. In this case, this is the Core i9 processor. This will probably an IA64 and x86 instruction set that executes that. So this is the typical thing that you know also from other lectures, as well as your own observations when you compile programs down, let's say with LLVM or similar things. Then you would probably have that. So we learned how to type check this, and now we want to type check this. And as you already might know, that these are not languages that are typed. Like x86 is a language that does not have a type system in itself, and ARM neither. So if the inventors of these instruction sets did not intend to for them to be typed, why should we now care, and why should we now type check programs produced by a compiler from programs that already type check? So isn't type safety a property that withstands the translation? Well, hopefully it is, but you don't know that. You don't know if your compiler is actually faithful in that sense, and if the type check is used at all. Sometimes you even don't know if you have a binary in some form that which compiler you actually used. For instance, any binary compiled for your Intel processor may be compiled by an Intel compiler, or maybe compiled by something like GCC or LLVM, to name just a few. And Microsoft also has a C compiler that might have produced this. So you basically don't know which compiler produced this. So you don't know if the compiler actually checked the type safety of the program before compiling. There is no evidence in that compiled program anymore. Yeah, and also there is no guarantee for type safety, or no hints for type safety in the compiled program, in the compiled code left, because of erasure. We talked about erasure, and that programs behave the same, but that says that we type checked them before. However, we don't know that this actually happened, and we don't have any evidence left in the code that this actually happened. And if you think that you downloaded programs from the internet, you probably have not looked into this code ever yet. And it would be nice to have some guarantees left that these are actually type safe. And also, sometimes you have some precompiled third-party code that you trust inside of your applications. For instance, if you do C++ programming and you include some libraries, you probably don't include them by source, but you include them by binary, and then you would have no control over the type safety of this third-party code, of course. No? And one thing that I already talked about in the last slide is the notion of mobile code. So our previously delivery mechanisms for software. So this is a few decades ago. So you probably will never have had this experience in your life. But it used to be that programs were delivered on data media, like diskettes, or like a floppy disk. So floppy disk is the English term, or CD-ROMs and whatever. So you had some data media, some physical media, where you can actually attach some tags that this is genuine, and people did so. I looked here around in my office if I still have something like a CD-ROM with a hologram that would be hard to forge, but I actually must have thrown them all away. So that's how long ago it is. So it used to be the case that we had some trusted sources, and we had some provable, genuine media that we could transfer them to the end user. And this has drastically changed, because now software distribution is currently you have basically two options. So you distribute some binary file that's compiled to the target architecture. This is usually what happens when you install some programs for Windows, let's say, or when you use a package manager for things like a macOS or a Linux. and you get a compiled binary file that is compiled to the target architecture. Or in the case of Java, you get a package that is like distributed in some intermediate language form. In this case, it's Java bytecode. Or for .NET, it's this intermediate language, it's the IL code, the CIL code, the Common Intermediate Language, that it's distributed on, and then just in time compiled to the target architecture. These are typically the two mechanisms you have, and then you download this code from the internet. And of course, there are some forms that you check for the genuinity of this code. There are some checksums, some signatures, and so on, so on, so on. But all of this is basically just a substitution for anything that you had before to kind of trust the source. But do you trust the code? You couldn't before, and you couldn't now. No? And we want to establish some trust in the code. And actually, this second part, this intermediate language form that is used for Java and .NET, has some advantages because you can reproduce some of the type check proofs for this intermediate languages before just in time compiling that, and actually the Java runtime does so. And there's some like language definitions in that, some terminology involved. We in mobile code, we typically call the system that received this mobile code and executes the host, and the possibly untrusted code is the so-called agent. So what happens for intermediate languages? So this is typically code in some high-level language like Scala, C#, Java, or your language. And then the compiler does not produce directly bare metal code, but code in some intermediate language that is, for instance, Java bytecode or .NET CIL. Any modern code platform seems to be going this way. With Rust now, we have a different option that they actually compile to bare metal because they want to be most efficient, and they believe they can do this in this way. There are some conflicting opinions on that, by the way. And then later on, so this code is then delivered. So when you download a jar, that is Java bytecode, and then there's a JIT compiler that then compiles to your machine. By the way, this is also true for very modern things like smart contracts that are distributed on blockchains. They also have an intermediate language that they are compiled to and then executed on the nodes via a JIT compiler. And then this is now translated to the JIT compiler then produces the bare metal code, the instructions that then run on the microarchitecture. There we go. Now the picture is complete. Good. But it also has the opportunity that you can JIT compile, of course, to other platforms if you want to run this code on other platforms. So the nice thing about an intermediate language is you don't, by compilation, fix the physical processor that you run on. The JIT compiler does that for you. So you basically do the compilation on the client machine itself. Of course, this takes some time, but you only need to do it once per program, and then you can reuse it, and then do all sorts of optimizations to it also. That's pretty neat. Interesting thing about intermediate languages, they all preserve some type information. They reduce some other, which is interesting to some degree when you do type checking. For instance, the intermediate language that LLVM compiles into the compilation process preserves a lot of type information and then loses it once you compile it down to the bare metal code. And the interesting thing is, if you have some type information you preserved, you can actually type check programs in the intermediate language just after you delivered them. So the client can actually do that and redo type proofs for the program, and then be sure to check things. This is actually what happens, and this has contributed a lot to Java's security. Java has some insecurities as well, or had some insecurities as well, but these were not it. If you want to have distribute a program without any checks on the client, then typically the way to go is to provide a binary format and then do that on the distribute that to some channels if you want some hacking advice. Again, please don't do this at home. Good. So this is then we consider mobile code, so code that is then just in time compiled. Yeah? And if you look at kind of the multitudes of software sources, the multitude of vendors that you use, and the openness of the delivery channels being the internet, you need to establish some new form of trust relationship. And that hosts, so the code that actually run the mobile code, that needs some strong guarantees in order to safely and securely run mobile code. This, by the way, are guarantees that you do not have if you compile down to the target platform and deliver that. So mobile code in the intermediate language gives you the opportunity to actually establish some strong guarantees. So how do we establish trust? One thing that I already hinted at is you can do things like cryptographic code signing. This is now included into basically any system. The knobs are usually like turned and twisted into a higher setting each iteration of your operating system, be it Windows or macOS or Linux. So code is cryptographically signed, so you actually know who is the culprit that sent you this, but you actually don't know about anything inside of the code. And this is the other way, which is like orthogonal. You can do both. Is that you provide the host, so the person like executing the code, with the proof of a property and some means to verify this proof on their own. And the idea that is behind that is so-called proof carrying code. You can do this pretty low for some basic properties, but you can ramp this up even to things like non-interference, as we've seen before. So what you do is you provide some form of a mechanized proof, so some output of your prover, of your type checker, that has been produced before, and some ways to verify that this program is actually related to this proof. The idea is that like the proof itself is hard to compute. The verification of the proof is easy to compute. And this is actually what happens to some degree with Java. This happened with mobile Java a lot. This happened with Android to some degree, but you can pretty much use that yourself. And typical properties for that can be memory safety. We will learn about memory safety today a lot. Type safety, in the sense that we learned it already, is some property that you can give out there. You can have things like bounded execution on memory usage. So you can basically do a proof that this code does not, let's say, use more than 12 megabytes of memory, and you can basically put this proof inside there and give an upper bound and let the client do a check, which might be helpful. Or the proper use of the provided API, you can also do the same thing. And this all helps you to establish trust in the code that you output. And the idea here is that like type safety or let's say for this lecture, the idea now is that we want to preserve type safety, and we would like the host to recheck before running this agent code, this code that we produced, and then the client can actually like recheck this. Yeah. And the idea is that like type safe source code is then mapped through a series of successive lower level intermediate language to target code. This is the translation part that we talked about it. And as it transformed the code, it also transforms the proofs. Yeah, so we preserve type safety and all these proofs, that these checkable proofs along compilations, because we translate them too. This means that type information, the ability to prove it, is then also preserved. We do not erase anymore. We actually provide you more than before in order to verify easily, and we translate this down. Just as an excursion, let's talk quickly about machine models. We have typically the two instructions models that you usually have is CISC and RISC, and Java and .NET CLI are both more or less CISC in their machine model. That means that their instructions can execute several low-level operations at once. And what we do today is a little bit different, because we are using a RISC-like architecture where one instruction is actually one operation and memory access is an explicit instruction. Yeah. In JVM and in CLI, this is not the case for some design reasons that I don't want to get into today. But just if you compare these two, what we do today is a lot more like a RISC-like architecture. So if you're familiar with these, the following will be very familiar to you. Yeah, and if not, this is a good way to brush up on machine architecture. And we'll dive into this right now. We'll develop a new language now. Not related to the lambda calculus, not related to anything that we had before. This is a completely new language. And we call this TAL0. TAL is for typed assembly language. And 0 is kind of the level that we assign it to. And in this language, we'll concentrate on one property alone, which is control flow safety. And control flow safety means that we prevent programs from jumping to arbitrary machine addresses and executing arbitrary code. And this means if we control that, we allow only a well-defined subset of possible entry points. And then we also prevent a couple of things that are related to jumping to arbitrary machine addresses. Things like return-oriented code and so on and so on and so on. We all prevent that by giving us a control flow safe language. What does control flow safety mean? This is a slide that I borrowed from my dear colleagues Eric Bodden and Martin Mori, that have prepared this nice slide on return-oriented programming. So in this you have to transfer your knowledge a little bit. So on the left side you have a C program, and on the right side you have the x86 translation of that program into assembler code. So this is rather unfamiliar territory from the things we had before, but just to see what happens there. These are like color marks, so you see this left scanf line translates to this LEA, MOV, and call functionality here. The next line then translates to these things, and then there is this return instruction there. And then you have like the function header and the function footer and so on, and you have this main function. So you can basically see what translates. Typically you can't. In this very easy example, we made it that you actually can. And then we have to look a little bit of what happens here and why we can actually use things and jump to different things. So first thing that you see is on the memory location, when you call this function, on on this memory location, the return address is denoted. And this is the address that you return to if the function leaves now the call stack. Yeah? And in this case, it's the return address here of this line of code where this scanf functionality is called. This is the line 7 in the C source code and the line 11 in the assembler code. Yeah. And as you can see, like the stack that you have here, it grows upward. Yeah. And users may override function pointers. So what does this give us? So in C, as a programmer, you can override function pointers, which means you can basically control anything that is on the memory. And you can do stack smashing. This means you can directly execute a user-controlled arbitrary code. This is typically not what you want. So if you are in a library and you want to call another function, this is typically not where you want to call user code. You want to call some other code for some other library or yourself. Yeah. And then you can override this functionality by something else and then overwrite this return address. So whenever this function returns, it does not jump back to the original point. So the next line in execution, so to some other arbitrary location. This is where you actually inject this address and then jump to something else. And then you can basically overwrite this with some malicious code on the stack and then execute anything of your own. This is how some class of attacks usually works if you have direct assembler code that works like this, binary programs that you can manipulate to some degree. Yeah. So this is a code injection attack that can happen in this case. And we want to control this a little bit now in our language and jump only to predefined locations and not to be able to jump to any kind of locations. So just a more close definition of what we mean with control flow safety. So without control flow safety, we've just seen that a malicious program can jump past any other security check that we might place in the program. And that gives us the conclusion that without any control flow safety, access control cannot be guaranteed. So whenever you have access control in a program, you typically have a branch condition or you call a function. And if you cannot rely on control flow safety, typically your access control is not worth anything. So whenever you see something like this in the program that has no control flow safety, it's actually not a safe way of implementing access control, because when you can jump to arbitrary programs, you can jump past any of the security check and just circumvent it. Yeah, it's this big Hollywood override button that you have in systems inside of programs, basically. Yeah. Not something you want to have. So what we will do now is we will do a model for control safety first, and then we will extend it to a more general sense of memory safety as well. So if you have followed the previous slide a little bit more closer, you have seen that we also inserted code into memory. This is also not something that we want. So this is also something we want to control in the end. So memory safety is a concern of us too, but we'll do this in TEL 1 and build this up step by step. So for right now, control flow safety it is. One thing before we start, we're working on an abstract machine and we're not working on a concrete machine. Even though we're dealing with assembly language, we do not yet attach this to concrete machine models, so something like x86 or so. We stay abstract. Specifically for labels, so labels we can jump to. Typically these are memory addresses. As you can see, these are arbitrary integers. Right now we will stick to predefined labels and not arbitrary integers, because it makes it easier to prove actually at this point. And we can later on exchange it if we would like to. We can do an application to a concrete model always later. And the distinctions between the abstract and the concrete thing makes the checks actually explicit. And then we can actually see where the difference between the abstract and the concrete actually are, and actually makes it more tractable to work this way. So we start with an abstract machine. So this is the syntax of TAL0. And let me quickly walk you through this. So what you first have is registers. You have a predefined number of registers, in this case K, so going from R1 to RK. And registers are things where you can store values into. And then you have operands, which are integer literals, so you can have any kind of integer in your program. You have these L kind of operands or values that are labels or pointers. And then you have R, which are again the registers. So registers itself are values. The instructions in your language are like this. You have assignments, direct assignments of values. So you have a target register and you want to assign a value. You can also just assign two target registers. You don't have anything like a variable here. You just have these registers. You can do adds, which always work like this. You have a source register. You add a value, which can be another register, as you can see, a label or an integer, and then you assign this to a target register. And then you have an if construct that says, okay, if for some register R, you can only use registers as as the condition for the if, then you jump to a value v. And then again, values can be labels, integers, or registers. So we see some opportunity for type checking here already. And then you can sequence, which basically tells us you can either do a jump, or you have a number of other instructions before. You have another instruction before, and then you have the I at the end, which also means that your terminal instruction will always be a jump. Because if you unfold this, the only way you can terminate the sequence is if you have a jump at the end. So any kind of instruction sequence always ends with a jump. So you have this fixed set of K general purpose registers, and the instructions are like simple assignments, additions, conditional jump instructions, and RS is the source register and RD is the destination register, as I just told you. Okay. Let's look at an example of this program. So you have here three instruction sequences. We label them. The first we call prod, which basically assigns 0 to the register number 0, and then jumps to loop. And then if R1, if register 1, then jump to done. This translates to if A is the contents of R1 equals 0, go to done. And then you take register 3 and add register 2 plus register 3 to that, which is basically res assigned to res plus b. And then you add a -1 to register 1, which is decreasing anything that is in register 1, so in variable a by 1. And then you jump to loop again. And then the done jumps to register 4, which is just basically the endpoint of the program. Not given here. So some else thing where you actually call this function. And as you've already guessed, this is a product function. So it takes basically two registers R1 and R2 and adds R2 times R1, adds R2 to R3 and does that exactly R1 times, so it's like a product of R1 and R2. What comes up then in R3. So what you do have here are input registers like R1 and R2. So you have like a pre-existing state, and then you have some register that is kind of your output variable that you compute, and then done you jump to some label back wherever you are. So this is an example in this language. We need a little bit more in the syntax than just this language. We need the machine model to actually work. So our syntax contains the entire machine here. So you have a so-called register file which assigns the current value to a register. So this is basically what you had in references, but this is not a heap. This is actually just a so-called register file for pre-compiled, pre-existing registers. You do have a heap, and the heap values are just code. So anything on the heap is code. That you can see if you look at this big H variable on the right, meta variable. This is labeled heap values, which are code sequences. So if you go back here on the heap, you basically have these 3 code sequences in the heap, and the labels for that are prod, loop, and done. And then you have a machine M, which is kind of a machine state, which takes a heap, a register file, and a current instruction stack, basically I, and this is the state of your current machine. So whenever you do a transition, you don't translate from one expression to the other, but you go from one machine to the other. Much similar than we had this transition from expression and the heap that we had before, the mu, the state there. We now have this, but like in a triple. And these are the semantic rules for Cal 0. And with the knowledge you have, this should be pretty straightforward. So let's look at them a little bit more in depth. Let me just drink a bit of water before. So you have this jump instruction, which tells you, okay, on the heap, on the translated register of a value, you should have an instruction set I. And if your machine model looks like this, you have a heap state H, a register state R, and the only instruction left in your current instruction set is a jump to a value V. Then your new state is the same heap, the same register, but the loaded code I that you load now from the heap at this particular register thing at this particular value. So you load code from the heap into your current machine. This is what the jump does. But look at, you only need to you only can have this one jump instruction left. It's not valid if you have more than that. Okay, then you have a mov instruction. A mov instruction is an assignment. Basically now you get a translation also from the higher level concepts like assignments and so on to lower level instructions like MOV. Yeah? This is basically what you have inside of assembler languages. If you have a MOV, this is an assignment. Yeah, because it's a move between things. But this is technical terms. Good. So how a move works, or how an assignment works, is that your current instruction on the instruction set is an assignment. You may have more. This is the I then afterwards. And your next machine state just pops this instruction from the instruction stack. So it's not there anymore. It's just I anymore. But you have changed the register file R and set the value inside of the register file, the value of the destination register to the unrolled value of V. Unrolled means because V can be also a register file again. You want to unroll this. You want to have the value. You don't want to do references to other register files. And you might have labels as well. Yeah. So you do want to resolve them to something. We will have a definition of this R with the little ceiling in a minute. Then you have the add instruction, which takes the source register and adds a value, and this basically works the same as the MOV, but you have premises here that give you the value of the source register, which is N1, and then the resolve value, which is N2, and then in the conclusion you see that the contents of the destination register are N1 plus S2. Good, and then you have two if instructions, and as you can see, if instructions just work here not by computing values, but just by executing jumps. And the way it works is, if the resolved condition register is a 0, contains a 0, then you execute the jump, otherwise you don't. And that you see only in the conclusion, where you have this little I prime in the if EQ and just the regular I with the without any prime in the if NEQ version. So what you do in the if NEQ version, if n is not 0 in this case, you just pop off the if instruction and go on with the next instruction. And this means you have basically branches in your control flow. What happens in the if EQ case, you basically load that code from the heap just as in the jump from the heap, and you exchange the instruction set in your machine model with this new loaded instruction set. Even though you might have other instructions still in I, you disregard them and just exchange the current code stack with the things that have been just loaded from the heap. So this R with the little ceiling on top is this just resolution of R for registers, N for literals, and L for labels. So how do we define type safety in something like this? I already mentioned that we now don't have expressions, but we have machines, and these machines should never get stuck. So that means that there must be an M prime always that I can resolve M to, or we have some value. We have some form of a value condition that terminates the program. So the key part of that will be how to handle these integer values to ensure that jumps can only happen to labels. For this we need to define a type system, and this is the type system that we want to define for that. So the basic things are that we need, the basic building blocks that we need here are things like type operands, and we use this tau to denote them. And operand types are things like word size integers, so the int type, code labels, and as you can see, code labels come with their own gamma, and gamma is a little bit defined differently here. Sorry for that, but you have to adapt to that a little bit. And then you have a so-called alpha, which is a type variable, and then you have something new which we haven't covered so far. It's a so-called universal polymorphic type. I will get you into this in a second, don't worry. Register file types are basically what you have in your head as record types. So you have a label and you have a type for that. So these are for register type labels and for heap types as well. So you type the register file and you type the heap. This is basically like your gamma and sigma typing as you had before. But have a look that code uses code is used for type labels. And when a jump to a label is executed, the register values need to be typed by gamma. This is kind of the typing environment of the code block. So this helps you to ensure that the input values to a code block are actually the same as expected by the code. Remember our example before where we used register 1 and 2 as if they were already initialized. This of course has some implications to the typing of the register file as well. So coming to this alpha, this is a type variable, and this is a so-called quantified type. This is a for all alpha dot tau. Sorry. We will do, as we did not discuss it yet, like the next slide, we'll have a quick introduction. So polymorphism works in a way like this. It allows you the use of a single piece of code without with multiple types. And parametric polymorphism, the thing that we now have on type level, introduces type variables that can be used to type a piece of code generically. So what does this mean? So this is the identity function with a new type. With a new type variable. So you can see it's lambda x dot x in essence, but ID now also takes another lambda which is used as the type of this identity function. So that means that the identity function works on all types that are given to it. So that means that the identity function is going from this parametric polymorphic type for all alpha dot alpha to alpha. So basically what you do is you say this function works for all types. This is the for all operator here, and we bind this type, whatever it is, as alpha. So the type of ID is alpha to alpha. So this means we do not have to have types for integers, for natural numbers, for longs, for whatever. We can just write a general identity function that works in all types. This is parametric polymorphism. And we call this a so-called universal type because there is a for all quantifier here. So for all types alpha, the type of ID is alpha to alpha. Okay, let's look at values. For this we have this big psi environment, and the typing of values is always like if you have an n. If you have like a number literal, this is always an integer. This is the s int ruled. And then you have the label rule, which basically is a recursion that takes you, okay, it is the psi type of the label. So labels are using the heap type environment to determine the specific label. So the rule only applies when the label is in the domain of psi. These are the operands of this thing. So it's typing for operands. So this is just register typing. This says, okay, you can type under psi and gamma, R as the proper type denoted in the register stack. Also see that like the psi here is mentioned, not used on the right, but it is a prerequisite. It is because for some rules we actually need it and for some we don't. The as-val rule basically tells you, okay, values you can type in the heap environment as tau, even though you have like the gamma premise. You just drop the gamma premises and just type in an psi. And this is the as-inst rule gives you the typing for code, and this is the universal polymorphic type that we just discussed before. But then in the conclusion you see a substitution. This is again a different notion for substitution. We talked about this last week, that there are different notations for that. So this substitutes tau prime, any occurrence of alpha in the type with tau prime. So these type judgments, they lift values, value typing to operands. So you have now the proper operand typing. So you have values, and then you can use them as operands if you apply these rules. Registers are given by that given the type assigned by the register file, that is gamma. Pretty straightforward. Then you have instruction typing. So instruction typing is that you have an I that goes from gamma 1 to gamma 2, because instructions change the register. They do not change the heap. As you can see, that means we can use psi on the left side. So under these assumptions of psi and gamma, if you have a value that you can type as tau, then under the assumptions of psi, the type of the morph instruction is a transition from gamma to a new gamma, where the register type of RD is then the type of tau, the type of the value. So you can actually change. This is a difference to reference typing that we had before. In register typing, you can actually change the type of the register file just by assigning. So this is a huge difference. In the add rule, this is basically the same. However, as it's an addition, you already know that the result must be an integer. This is pretty neat. And the conditional jump, so the if rule for this, is pretty neat. So you already know that the you take the premise that the source register here, the condition register, must be an integer, and the value must be of this type code gamma. So under the current typing, under the current register file typing, the code that you jump to must work. And this is the key thing here that allows you to only jump to locations where the expected typing of the code block matches the input typing at that particular point in the execution. And this is just a jump. It's just a function going from gamma to gamma in this case. How does it go for sequences? Well, if you have a jump, then you the type of the jump has kind of the code typing of the target. If you have a sequence and the instruction is kind of a transitions from gamma to gamma 2, then the next instructions must be typed as code of T2, and the whole thing is then code of gamma again. Yeah. So the next instructions must also match the assumptions, like the outcome of the current instruction. And this is the chaining basically inside of a code block, that all of the proper register typings in one line must match, then like the outcome of that must match the expectations in the next line. So that means that you cannot have anything used in a different typing way than you actually it actually makes sense. And the last rule is basically helping you with the reduction of universal quantified types. That means if you can type some instructions as tau, you can also type it as a universal quantified type, and say for all alpha dot tau. Good. This is the typing of the complete register file. It's pretty straightforward. So we say that for all R, if under the assumptions of psi, you can type their register content as the register file type, then the whole thing is well typed. So this is just a summary of the complete register file that helps you in that. And heap's basically the same. However, the heap typing must actually describe like psi. Yeah. Free type variables. This is the FTV. So these are just free type variables, and there must not be any free type variables in the heap typing at a certain location. Yeah, and that is true for all locations in the domain of psi, and for all the locations in the domain of psi under the assumption of psi, the heap typing of that particular label must match the psi typing. So this is where you basically bind them together, and then you have a well-typed heap. And then you can sum this up. Now we're building this from bottom to top. So a well-typed machine under no assumptions is composed when we have a well-typed heap, H, that is well-typed as psi, and under the assumptions of psi, the register typing is also well-typed, and the instructions are typed as code gamma under the assumptions of psi. How does this work in action? Let's have a look. It's always good to see this in action. So let's go with the first block, and you actually see that the assumption here in gamma is that R1, R2, and R3 are integers, and R4 is a unified quantified code that is for all alpha, and then this is a code typing, which means that R1, R2, and R3 are of type integer, and R4 is an alpha. So that can be any other code. This is why we need the universal polymorphic type, because we can use this function that we just written, this prod function, basically this whole block of code, at any other point if we match the assumptions given here. So this is why we need this alpha, so we can basically use any kind of code. Let's use this type because this is kind of the most interesting line here. Let's type this first. So under the assumptions of psi, if R1 jump to done should be gamma to gamma from the rules. So we use the as if. So the premises are under the assumptions of psi and gamma. R1 must be of type gamma R1, which is int. We can just look this up in gamma. And then under the assumptions of psi and gamma, we have a done, and done should be a code of gamma. We have to look up done previously, but first start from the left side. We use this sreg rule, and this sreg rule gives us that because we can just use it up. So on the right side, we need this sval rule that tells us, okay, under the assumptions of psi, done is typed as the type of done in the heap typing, which is code gamma, which matches, and we're good. And just see that all the gamma just works together. And for this, we need to use the slab rule and find that. Oops, now I lost that. Sorry for that. And this is then given by the label rule, and then we have our derivation tree complete. Now, of course, we also need to check inside of gamma and so on if all of this is well typed. I'm omitting this here. So what else do we need to check? Addition needs to preserve gamma, and subtraction needs to preserve gamma. So addition says like, okay, we go from R1 to plus 2, R3 equals now R2 plus R3. This goes from gamma to gamma. Let's use the sadd rule and say, okay, R2 must be an int, this is given, and R3 must also be an int, this is given. By the sreg rule, we know that this is true when we look it up at gamma. And for the subtraction that we have here, this should also be the case, and we check that -1 is an integer and that R1 in gamma is also an integer. We need to use sreg again, and then we're good. Okay. For this other rule, we need to use the sval rule and then the sint rule, that we actually come to the same conclusion, but this is just technically, you've seen before that -1 is an integer. And finally, we need to type check the jump back to the loop label. This is the only line of code that we haven't type checked yet. So let's look at that. So use the sjump rule, and they say, okay, under the assumptions of psi and gamma, loop needs to be typed as code gamma. And then we can use the sval rule and find again that our heap typing contains that loop is typed as code gamma, or can be typed as code gamma, and then we're good because we don't change the register assumptions here. Slab gives us that, and then we're good. And if we now string all the subproofs together using this S sequence, we can now confirm that we have a valid heap typing for our complete instruction set I for the complete program. And the only thing left now, so we've seen it in action, we've seen the definitions, we've seen how it works. We need to prove that the system here designed actually enforces our desired type safety. We have said that we want to reduce stuckness as our error flag, and we have to show progress and preservation. And for this, let's introduce a couple of lemmas again, and then we show the soundness of the system as we're used to that. So type substitution is one of the lemmas like this. See, the definition numbers now correspond to the advanced book, not to the basic book again. This is why we started 4 to 6 again. It's mentioned on the first slide, but just to denote it here. And as you can see here, we have some type substitution lemmas that carry the type substitution from the rule a little bit upwards and say, okay, if we have, then we can substitute t with alpha, alpha with t in gamma, and in the particular values, and in function types, and in label types, and in register types, and so on and so on and so on. This is just an application, like an version of this what we've seen before for type substitution. So here we established that derivations remain possible after substituting types for type variables. So we can always introduce new type variables. And this is the key issue because, as you've seen, we use universal quantified types in these code locations. We need to be able to lift kind of concrete implementations always to the things where we have type variables. This is the register substitution lemma. It ensures that typing is preserved when we look up a value in the register file. So a lookup does not change the typing. And this is basically the same thing as the value substitution lemma in the soundness proofs for conventional lambda calculus. We've seen this before. Good. We need a canonical values lemma again. So if we have a well-typed heap, and in this heap typing we have a value that is typed as tau, then either tau is an integer for when the value is a number for some number, or we have a code typing in the heap because we can either have values or numbers on the heap. And if the value is a label, then of course the type of the label is a code typing, code gamma, for some L on the domain of H, and it must be the same that in the heap typing the heap location of L is then typed as code of gamma. Yeah. And this lemma tells us basically what kind of value we have from its type. Yeah. So we can either have integer or code typings on the heap. Here we do have not only values, we have operands, so we also need a canonical operands lemma, and this is basically the same thing. This tells us the same thing, that we have integer typings and code typings for these operands, if we have operands involved. Nothing really fancy. And then we can define the soundness of tau0 as like this. So if we have a well-typed machine and there exists an M prime such that M evaluates in one step to M prime, so this basically tells us if we have a well-typed machine, there's always a next state, and this next state is also well-typed. Yeah. So that means that it is typely, it is sound. In the interest of time, I'll quickly go over this proof. We have the time. So suppose you have this machine consisting of the heap, the register, and the instruction set, and it is well typed. And by the inversion rule of the machine rule, you have a heap typing and register file typing such that all of these things exist. And then you actually do only need to prove induction on I, because the other things are just like sets. You can't do anything with that. That's typically fine. And you do a proof on the induction of I, and then you use the other things in this proof. So then you do a case-by-case induction again. So what can you have? You can either have a jump. This is the kind of the simplest form of an induction form, and for this you use the C inversion up here, kind of the code typing, and you use the inversion of sjump, and then you come to this conclusion. And from the canonical forms lemma, you know that there must be an I prime that exists on the heap and that is typed according to the same assumptions as here. So again, code gamma. And then we will see that we have this M prime as HR and I prime, And now we can show that m to m prime via the so we take now we construct now an m1 using the jump rule, yeah, and then we must show that this new machine is well typed. But this follows very immediately because you can just like use the same types, and you had the well typed thing before, and it is the same type. Like I and V have the same typing, and you can like follow this pretty immediately. So assignments, quickly do those. So you invert the sequence rule again, and then you have, because you have this I prime still in there, yeah. So then you have that this assignment is going from gamma to gamma 2, and the heap typing of under the assumptions of the heap typing, I1 must be kind of a code having the output assumptions in the register, so gamma 2 for some gamma 2. And then you invert the SMOF rule, and that gives you that the that this gamma 2 must be the new gamma, but now the type of the register type is now this new type tau for some t. And if you use the register substitution lemma, you come to this tau again, and then you take this new machine m prime that you construct by using the new register set and the I prime, and you can use just the MOF rule, the MOF evaluation rule, and you come to this conclusion. So it's just mechanics, as you can see. And then you can take the rec file rule, and then you conclude that this new typing is this gamma typing by construction. I quickly jump over this. The thing for the addition works basically the same, but you have like these value rules in there as well. But in the end, that doesn't matter. It works the same as assignment, because basically it's an assignment. You just need to do more prerequisite checks. But basically it's the same. So you have now the conditional jump, and there you have these two subcases with the if EQ and the if NEQ. But again, you start with inverting the sequence rule, because you have this I prime in there as well. And then you have this jump, which basically is again like a gamma transition. And this new sequence needs to be of code gamma 2 for some gamma 2, because if we do not execute the jump, the next instructions must match. Then you invert the SF rule, and then you get to these, and then you see that gamma 2 must be gamma, must be the same, because the if does not change gamma. And then you take the canonical operands and then you learn that like L2 and L, so you take two labels, and you see that L2 must also be typed as gamma, code gamma, and then you take the canonical operands lemma again for the register access here, and then you have the two subcases for N0 where you take the root for if EQ, and then you have like the MRI2, and then if it's not the case, you have MRI prime, so the actual jump. Not the actual jump, executing not the actual jump. So in either case, you can take the well-formedness rule for the resulting machines, follows from the S machine rule, because you don't have any change. You just have rewrites. Good. Okay, quick over this proof, very quick. Sorry for that. But as you can see, it's only very mechanical. You can follow this thing basically step by step and just invert the rules and do this. The thing is, the rules have been and the lemmas have been crafted in a way that makes the proof really easy. That's why the proof itself is not very interesting. That's why I spent more time on the lemmas explaining them than on the proof itself. So don't be confused by that. Good. Before we close for today, just a simple addition, which is TAL1. And this is called simple memory safety, what it adds to the game. And as you can see in TAL0, we could not allocate any data on the heap. And this is in practice not very helpful. And we would like to support this as well. But we would also like to guarantee so-called object level memory safety. And that means that no memory access should read or write a data object at a given location unless the program has been granted access to that location. Yeah, so we have access to certain memory points. Example program again. So here you have kind of the preconditions, and here you see that reference 1, the register 1, is a pointer to code, to some code. And then we see that register 0 is initialized by 0, and then the memory of register 1, which is a pointer to code, is set to R3, and then we jump, then we store the memory location of R1 into R4, and then we jump to this location. So we just written a 0 at a memory location that should contain a pointer to code. Yeah. So this should not happen. We also need to take care of aliasing, as you can see here. So we can have two registers that point to the same code. We don't know that. But should this type check? Of course, no, it depends. So if R1 and R2 point to the same location, we might have a problem. If not, that might be okay. If we don't jump to that, who cares if you overwrite code? This is also pretty neat. And in order to do this, we do have two separate classes of pointers. By the way, we will take a little bit of an overtime today, but as we've did a little bit of less time in the last week, I think it will compensate. So we have two different types of pointers, two different classes of pointers. We have so-called shared pointers, where aliasing is freely allowed, but the types of the pointers must be invariant. So whenever we assign something to a shared pointer, once the type is fixed, but then we can't do we cannot change it anymore, but aliasing is freely allowed. And then we have so-called unique pointers. They cannot be aliased, that's why they're unique pointers, but the type of the pointer can change. So this is quite the same as registers, but on the heap. And syntax additions are like this. So you basically have the same thing as in TAL0. And you do have a little bit more. You have load and store instructions. This is the RD-mem instruction and the the mem equals RD instructions. Always look that you have a source register and an offset. So you can always do a little bit of pointer arithmetic here. And that you have an explicit malloc instruction here that gives you n words. And this is the offset that you can calculate. This allows us to use it for arrays as well. You can take a register, which is a unique pointer, and make it shared by using commit. And on the right side in the values, before I explain the other things here, you have now registers and literals again. But L now points to code or shared data pointers. Shared data pointers are in the same vicinity as the labels, as the code labels, but unique pointers are not located there. So this is a difference here. So unique data pointers have this UPR value thing, and this can again then be a heap value. Then you have this salloc and sfree instruction that allocates so-called stack words and free stack words, and there is a special register sp for stack pointer, and this salloc and sfree increment and decrement this register, so we can model a stack. So we can actually allocate things on the stack. We will see this in the program in a second. No. Heap values again can be instructions sequences, and then tuples of values. This is the allocate n words thing. So tuples of values can be allocated on the heap. So not every location is just one word, but multiple ones. This slide seems very intimidating. It is the operational semantics of TAL1. We will have an exercise on this. There will also be a lab on this, so don't worry if you don't get them at once. You will step through them. I will just introduce you to a few of them, and you will make up the rest as you go. This pretty much works. By the way, is this... Okay, yeah. So we can spend a little bit of time on that. Good, so MOF gets a new thing. So the move operational semantics that we had introduced in TAL 0, which all of the rules still apply here, gets a new thing, a new premise that tells us basically like the resolved value of v cannot be a unique pointer. Yeah. So whenever we assign something to a register that cannot be a unique pointer, that allows us to limit aliasing in this point. So remember, we had aliasing via registers. malloc, so memory allocation, gives us a unique pointer of this length m, in the register. So a register contains a unique pointer of this length n. This is what malloc does. And then you have the commit operation, which makes from a unique pointer a shared pointer. So it moves the thing from the register. So the data is then moved from the register to the heap. The destination register may not be the stack pointer, because then we would override our stack pointer. This would be catastrophic. And the heap should not already contain a new free label L that we use. That's just a new free label. And then on the left machine, on the initial machine, we have a commit operation on the instruction stack. And a unique pointer in this register RD. And what we move is then we move the contents of the unique pointer, so this vector basically, into the heap that's on the right side on a new memory location L, and then mark that new memory location L in the register D. So we basically move the contents out of the register into the heap. Remember, we do not have the same operation to go back, so we cannot make a shared pointer a unique pointer again. So it's always a one-way street. Good. And then we have load instructions, which basically gives us the values at this particular point in the vector on the heap. So a committed, now shared pointer, we can read with this mem instruction, with this load instruction. And output it to a register. So let's say you see in the premise, you see this HL, which is kind of this vector n plus m, so it can be more. So it does not need, it only needs to be at least n long, but it can be longer. So you don't know the exact length at that time of access. So you take anything, at least needs to be as this long. And then you load it inside of the register. You can also load from a unique pointer, but then you don't look at the heap, you look at the register value, and then you just take this particular point in this thing. Also can be different lengths. Store instructions basically work the same. So if you want to store something at a particular point in this vector, you can freely do so for shared and unique pointers. This is absolutely okay. And then you have this salloc and stree instruction, which, as I said, manipulate the stack pointer. So you can actually model a stack in there and use the values at this particular point. So in this, you see the stack pointer is then modified, and there's like a max stack variable that helps us not to overcrowd this a little bit. We need this for technical reasons, by the way. So an example to get things a little bit more flowing. So you have this this copy, this code copy, and the register typings are given above and below. So the things before and after. And before, you expect R1 to be a pointer to int two word vector of int and int. And then you have two other registers, R1 and R3, which are just integer variables. And what happens then is in the outcome, R2 is now also a pointer with this two word integer tuple here, and R3 stays in it. So what happens is you take R2 and do a memalloc of 2. So you allocate this memory. So you allocate this unique pointer, and then you take the memory location of you take the contents of R1. So on the first word, and you store it to the register, and then you store it to the new allocated unique pointer in R2. And you do the same thing for the second word, and then you commit R2, so you make a unique pointer to a shared pointer, and then you have like this pointer to this memory location of int. So this is how you do basically a copy procedure in this. Typing is very straightforward. If you understood tile 0 typing, tile 1 typing is pretty straightforward, because you just have 3 new operand types, which is the shared data pointers, the unique data pointers, and you have a unique, you have a quantification over all allocated types. So basically the same as before as the code typing, but now for this code allocation typing. And what is an allocated type? So something that you can do inside types that you can do in a shared pointer, unique pointer. You either have an empty type, or you have a value type, or you have adjacent types. So you can just do like chains of allocated types, or you have an allocated type variable. You don't need to have actual types. You can use type quantifications for that as well. And there's a difference here. Alpha can be used to abstract a single word size type, and this I think that's a row. Me and Greek letters, sorry. I think let's call it a row. This little p like symbol here can be used for types of arbitrary size. So alpha is just one single word size type, but this row can be used for types of arbitrary size. So you can have like vectors of type variables. Good. Heap values and operands. So you have new rules for tuples on the heap and unique pointer operands. But as you can see, they're pretty straightforward. They just give you, okay, tuples are typed as sequences of types of their types of contents. So basically just in a record. And for the type of the unique pointer, this is just a vector of the value types in the heap. for unique pointers. Good. Instructions, instruction typing is so straightforward. Let's quickly go through this. What is one of the interesting ones? Let's maybe do the LDS rule for once. The new thing is here that you now have these two types, pointer and unique pointer, that we haven't introduced so far, but used and seen in action a little bit. And these pointer types distinguish now shared and unique pointers. Unique pointers are U pointers, and PTR are pointers inside of the heap. So the LDS rule again relates to loads of shared from shared pointers, and LDU relates to loads from unique pointers. And as you can see, they are pretty much the same. However, you have this little type quantifier in there that can be kind of a vector of more types. So again, as in the operational semantics, you do not make any assumptions after n. You do just make assumptions towards n, or at this particular point n. At this point, so you can load something that is in there and exchange then the type inside of the register file with this new type that you just loaded. So it's pretty straightforward from what you intentionally think about this. Good. I won't do a proof for that because it's again rather mechanic, and as you can see, there are lots of more additions. I mean, this looks like a lot, but it actually isn't. It follows pretty much the same principles. So these load and store instructions are pretty much the same, as you can see just by looking at them. The salloc and sfree rule are a little bit different to model the stack, but as you can see, this is just work the same thing as unique pointers of integer type. So it's just a special version of this. And the commit is just basically changing the types from unique pointers to shared pointers. The alloc just allocates something on the register in the register typing, a unique pointer in the register typing. So have in mind, you always start out with a unique pointer and you have to commit it to make it shared, to output it to some other function. Otherwise, it won't be possible to use. Good. Slightly over time, but I close with this set to literature. So what we handle today is basically chapter 4 in the advanced types book. In the types and programming languages book, if you want to read up on polymorphic quantified types, this is chapter 23 in the types and programming languages book. I took that from there, but only the things that we actually need to make it useful. The original paper from Greg Morissette and others is the from System F to typed assembly language thing in the ACM transactions on programming languages from 1999. You see, quite okayish, not as old as one might think. And then another shout out to another paper from, the same team of authors, I would say, a little bit differently. They make a realistic typed assembly language based on x86. Which transfers kind of the theoretical part to practical parts. I did not include anything in my lecture today from this, but if you're really interested in how this relates to practice, this paper gives a very good overview and is pretty much complete. No one attempted to do this for more complex instruction sets like IA64 or even more ARM, what's now 7, I think, instruction sets. Nobody did that yet. But if you feel that it brings you something, you can do this and research this. I think no one did that. I have to check. I didn't follow it so closely. Just in summary, what we learned today, we looked at typed assembly languages. just a quick one walkthrough. So we talked a little bit about compilation and why we might need types on the lower level. We talked a lot about trust and mobile code and so on and so on and so on. And this is actually why we all did this. Yeah. Because then again we have some information on the code inside of the code itself that we can again check afterwards. Yeah, so this is the idea of proof carrying code and types preserving compilations that we used. I motivated tile 1 and 0 also with return-oriented programming, and a thing to prevent that maybe in practice. It has not been shown that it's actually practically applicable, but in general sense it should actually work this way. In a sense, the idea of tile 1 and 0 has influenced pretty much the design of Java bytecode. So Java bytecode is control flow and memory safe because they preserve all of these properties and have an actual proof for that. So this is one thing in Java bytecode that has actually been proven, and that is quite reliable. So in Java, you cannot do arbitrary memory access unless you use these unsafe features in there, but in the general language you cannot do this. And you also have control for safety. You cannot jump to any arbitrary code point. You need to have a function call for that. And the reason for this is basically that the Java bytecode has the same properties as tile 0 and tile 1, namely control flow safety, what we learned today with this, let me see the type system again. Semantics, operands, there we go. Instructions, there we go. So this typing of sequences and if instructions here in tile 0 has helped us to make this happen, yeah, and to give this that we can only jump to things that are actual code locations by construction. So we cannot store anything else, and it's actually compatible in tile 1. When you store values on the heap, you basically have the same thing. And then we did a little bit of a proof today to actually show that this is type safe, and we've seen that this is pretty mechanical. And then we extended to memory safety, so not being able to read and write data objects unless we're granted access to that. We've seen that aliasing might be a problem here, and we did this again by constructing unique and shared pointers, and in the semantics and the typing of things constructed in a way that we could not do this. Good. Unfortunately, let's keep it short today and relate the questions to Panda. And I think you will have a lot of more questions when you try to apply this, either in the lab or in the exercise that will come up on this topic. With this, I'd like to close today. I wish you a very grand day and thinking about the things that we talked about today. Thank you very much.